Greetings to all our participants. I welcome you to the IEEE Virtual Talk Series 2020. And today's talk is being organized under the AcSIR-CSIO, that is Students Affairs Council. And this talk is being organized in the IEEE week. So I welcome you to another session in the series of these webinars. So today we have with us Dr. Jobin Varghese. So he is a scientist and a material and technology expert at the Fraunhofer Institute at Germany. So briefly introducing our speaker, so his current research area is materials for microelectronic devices and microwave applications. And he is a doctorate from CSIR NIST, Kerala, India. So he's an alumni and a member of CSIR family. So he has more than 32 scientific publications with H-index of 14, and he has attended more than 25 international conferences in many countries, including Finland, Germany, Portugal, Belgium, Sweden, US, Japan, South Korea, and China. He has 2 patents into his credit, which are based on silica-based self-healing inks and zircon-based HTCC technology. He has edited more than 5 books, 1 monograph, 4 book chapters under various publishers like Intech Open, Elsewhere, Springer, Wiley, Lambert, Academic Publishing. He is the guest editor for Frontiers of Material Journal, and he has reviewed more than 17 SCI journals, reviews, and book chapters. And he has project collaborations and experiences with Google, Horizon 2020, Meranet 2020, BF, European Research Council, MIT Fab Lab, DRDO, ICDD, etc. So with this brief introduction, I present a red carpet welcome to our today's speaker, Dr. Jobin. Yes, over to you, sir.
Thank you, Aduma, for the nice introduction. And today I would like to, first of all, I will say thanks to the organizing team. So as an alumni member of CSIR, I can say it's a good initiative to start with this kind of membership, this organization like student memberships and all those things, connection with IEEE and AcSIR. So I first of all thank you to the organizing team to inviting me to deliver my talk. And basically I am planning to talk today about my experiences, how I reached this sustainability in 6th generation electronic devices. Through my research career, I will talk about my doctoral degree a little bit and how I will reach the current situation and all those things. And we'll go to the next slides about the outline of the presentations. So always, most of my research career, so I have nearly 10 years of research experience, starting from 2019 as a project student at CSIR NIST, and thereafter I qualified CSIR SRF, and then I started my PhD from CSIR NIST. So when we start with the outline, I can say something about my PhD life in CSIR NIST Trivandrum, then research at University of Oulu, Finland as a postdoc, and then presently I am working as a scientist at Fraunhofer Institute of Ceramic Technologies and System, Dresden, and it's the eastern part of Germany. And my recent research activities on 6th generation devices and focus of strategic research in 2020 and research visibility, and finally I will come back to my personal zone. And I always like to do my research focused on sustainability and circular economic concepts. So that's why the picture shown in the left hand side about the sustainable development of movement towards the earth, how we can protect the earth nation and by sustainable way of doing research and all. So I would like to start with my first doctoral studies Basically, I started from 2019 as a master project student at CSIR NIST with Professor Sebastian. He is actually, my background is I have done my master's in applied electronics. Basically, I am an electronic master student when in 2008. During that time, I got accepted for doing my master project at CSIR NIST, and I have done some master project, and my supervisor, Dr. M.T. Sabari, is well known and a retired chief scientist from CSIR NIST, Kerala, India. And he is inspired, or he is teach me to get in this topic of material science, because I am new to this topic, because my background is basically on physics, electronics, and nanotechnology. These are the my graduate and master's courses I have done. So after successfully completed my master degree, I have started to look for a PhD topic. So then I attend one workshop which is regarding a Indian Rare Earth Limited. So it's a material manufacturer. They organize some workshop there. So my supervisor attended that, and they have given a sample of their minerals they have mined in various parts of India. So he gave me one packet of powder. It maybe look like, you can see that it's like a sand. It's a beach sand. Its chemical name is a zircon. It's basically zirconium silicate. So I take that beach mineral sand to explore its applicability in electronics and some technology, like I fabricate some kind of technology, laminated structures at very high temperature, which is useful for high frequency applications. Then I made some devices and antennas based on that substrate, and I made a ink out of that sands, and I give some more technology aspects like self-healing properties, and finally I print CSR emblem with that print with the conventional screen printing technique. So these are the my PhD stuff. So I just want to show you my PhD activities during CSIR NIST. So during that time, I have filed 2 patents, and it's granted about zircon and self-healing, zircon HTCC substrate and self-healing inks. So there is some initiative towards the sustainability in my research. So this beach sand we are directly taken from beach and extracted for some electronic and hybrid micro applications. That's the main start of sustainability usage of material from the earth. I start from there. So still there are many issues which is targeted towards electronic waste and sustainability for many areas of research and many electronic products. So the compilation of many material and all these aspects we need to include. I try to include in my research career, and this is our institution in Trivandrum, CSIR NIST. I move to the next slides. So after awarding my first doctoral degree from India, I got an invitation from Professor Heli Adunan. He is one known professor in Finland, and she invited me to work as a postdoctoral fellow at her group. And basically, there my topic of research is ultra low fabrication temperature materials. So the basic idea of this research topic is to reduce the fabrication cost of electronic materials and made at a very low temperature, below the current limit of the electronic fabrication technology. So here also still focus for electronic wastages issues and also sustainability and recycling, all this kind of aspects I done in my postdoctoral research. So end of the postdoctoral research period, we plan to make a second doctoral degree on topic of ultra low fabrication temperature. Then I awarded a second doctoral degree from Finland. This is my second doctoral degree defense at University of Oulu, Finland. It's a northern part of Finland, northern region of Finland, close to Arctic Circle. So during that time also I joined with a MIT Fab Lab for joint proposals for making, it is like a hobby proposals, like making bicycle energy harvester for low power electronic gadgets. So basically it generates some kind of, I just want to refresh my study topic from my master's and graduation time. So there basically the topic is to sustainable way to look for the energy. So that's why I choose bicycling. I like bicycling. I choose bicycling. How we can utilize this energy to convert as a heater. So anyway, you all know that we can use this dynamo for working as a to convert energy and use for some kind of light which can use for our cycling time. So basically I try to make a AC to DC adapter converter based on a microcontroller circuit and some kind of 3D printing and lasering as a value chain for this project to make a, finally I succeed to make a to store this energy from the bicycle dynamo to a power bank, and we can utilize this energy for many other, we can charge our mobile phones and many other electronic gadgets with power bank directly. So this is I partly done with during the stay in the Finland. So I awarded one diploma from MIT Fab Lab Academy during 2019 for this work. And now I move to my present destination, that is Fraunhofer Society. Actually, Fraunhofer Society is like our CSIR in India. Fraunhofer has 72 institutes spread over the India and basic research in Germany, which is focused on applied research. And the name of Fraunhofer Society came from a well-known scientist and entrepreneur. It's a Joseph von Fraunhofer. He is basically developed today's solar spectrum with a dark region. He explained the physics behind the dark region of solar spectrum. And also he has he started to initiate as an entrepreneur to develop a spectroscopic industry in Germany. Based on his contribution to the society and science, our institution, the Fraunhofer institution, make honor as his name as its society. That's Fraunhofer Society, and currently 28,000 of employees, basically scientists, engineers, technical staffs. These are our strengths in the institution, and annual research budget is nearly 2.8 billion euros. And our basic vision about the science and applied research are basically we focus research on bioeconomy, intelligent medicine, resource efficiency and climate technology, artificial intelligence, next generation computing, quantum technology and hydrogen technology. And most of the impact is focused for affordable health, complete energy transition and resource efficiency, climate technology, security, resilient society, and digitized value creation and integrated circular economy. So basically, we offer our applied research support to the society from first generation to the coming sixth generation technologies. So here you can directly see that science is closing towards the nature creation, and that's the agenda for Europe to make a sustainable economy and a circular economic and sustainable value chain for the sixth generation electronic device. So that is basically my current topic of research today I'm going to discuss. So basically, I am one among the institute, that is Fraunhofer Institute for Ceramic Technology, IKTS, that is situated at Saxon State, and we have nearly 700 employees for Fraunhofer IKTS. We are giving basically our organization is basically a research center for a ceramic material, one of the highest research organization for Fraunhofer Society. We have a 700 employees and three different states as Saxon regions. You can three main different sites at Fraunhofer IKTS, and our value chain and social beneficiaries to many applications are ceramic microcircuits, pointing towards communication component, defense and aerospace applications, microsystem, medical technology, automobile and packaging, industrial electronics. These are our beneficiaries. We utilizing our ceramic research to bridging between the industry and academic life in Europe, especially in Germany. So, I'm part of a Department of Hybrid Microsystems group, and so here we are developing a ceramic thick film and multi-layer technology, basically made up of many electronic devices. Today's our handset to many other electronic and consumer electronic products. Basically, we are playing with high reliability materials, thermal expansions, rough environmental aspects, how operating conditions are affecting the device performance, and also high thermal conductivity for dissipating heat. And these are our main components and value chains for industries. And we basically reference automotive, industrial electronics, and power electronics sectors based on various kind of ceramic components, materials, some semi-finished components, and many devices, which is playing wireless communication and many application areas. So basically, you can see the multi-layer ceramic technologies are in different sectors. I will explain more about the evolution of this technology, how it is coming, and what are the target goals, and how the origin of this technology, and what is the present situation, and how we are building a future with these technologies. Basically, you can see from that there are multi-layer of ceramic packaging technology embedding with silicon carbide and other integrated circuits to making value chain for many other applications. So basically, we developed the technology for HTCC, LTCC. HTCC is a technology for high temperature coated ceramics, that is above 1000 degrees Celsius till 2000 degrees Celsius. That is a high temperature coated ceramic technology. Then the next technology is the low temperature coated ceramic technology, that is low temperature fabrication. The temperature limit of fabrication of LTCC is 800 to 1000 degrees Celsius. So this is reducing the price of the devices. It is down because of the fabrication temperature is less as compared to HTCC technology. So we are till now we are moving with the existing technology with the HTCC and LTCC, and we are offering many gadgets and many electronic components and semi-finished components for the electronic and microelectronic sectors for various applications. So basically, our department main applications are substrates, sensors, components, and green energy systems like solar cells and SOFC and batteries, solid oxide batteries, and heaters, LED packaging, and mechanical different sensors like mechanical, thermal, and chemical sensors, and standard thick film technology for the fabrication of microelectronic circuits. So now I would like to talk about what is the idea behind our recent technology, how we are approaching that technology and all. So for that, I would like to show you a world map which represents the carbon dioxide emission high in the worldwide. So from this slide, you can see that who emits the highest carbon dioxide emission in the world. You can say it depends upon the automobile pollution and also industrial development. You can see that among the global, the highest, the red region is the main targeted area, which is higher pollution of carbon dioxide emission. So how the countries like Europe and many other countries, how they are trying for the future generation with less carbon dioxide emission. So that's the main agenda behind this slide, to show how these countries are developing their sustainable future for our technology, the surviving for the new technology to grow the world and society. So here the initiative from German, basically from Fraunhofer Institute, you can see from this red circle here, the highest efficient solar cell that we have developed at Fraunhofer ISC in our campus, that is the highest solar efficient solar cell which is developed with a 47% of efficiency. So this we have developed at our institute, and these are the most highest efficient solar cell. Now various parts of the world use this technology for various applications, for converting solar energy to electrical energy and so on. So this is the targeted development in the how they are reducing an alternative way of energy source to achieve reducing other carbon dioxide emission during the energy production and all those things. So for that, I will explain about the energy sectors of Germany, how they are achieving these goals. You can, this is a 2019 report of how they are producing energy. So you can see that Germany is reaching nearly 50% of energy production from renewable source. So basically, the energy production from nuclear is very high in Europe, because they have many nuclear plants. Because of the high risk of nuclear safety, they want to reduce or zero nuclear power in the future. That's the reason they are reducing, and they are looking for alternative power source for the future generation. So the renewable energy, basically they are focused research on wind offshore and hydropower and biomass, solar cells and others. These are the main sectors of their power, renewable power source in Germany. And other sources have natural gases and hardcore coal-based power production, lignite-based production. These are one of the source which is generating high amount of carbon dioxide emission. Of course, the automobile population is also generating high amount of carbon dioxide to the world. So we want to reduce this carbon dioxide emission. So all the focused research in Germany are focusing towards the sustainability and circular economic usage to reduce electronic wastage, and also balance the power production to control the carbon dioxide emission in industrial sector as well as power productions. So I'd like to move to our new and running project about Astrobat. This is basically this project, our part is to develop a high strength batteries, that is solid state batteries, which is having capacity of 1000 kilometers at one recharge. So this is our target goal. So we will deliver our first battery production for the different automobile sectors in Europe to develop the high capacity batteries in 2030s. So we have nearly 15 partners around the Europe to involving this project, and I am also active in this project representing from Fraunhofer IKTS. We are the manufacturer of batteries, and we will make a 3D printable batteries for the next generation electronic vehicle. So we would like to integrate more electrical vehicle in the future. So I am welcoming all you to see some of our videos recently based on our project. So basically these two generate new electric vehicles for automobile sectors. 25% of EU emission we can control by automobile pollutions. So this strategy should be focused for the future generation sustainability and eco-friendly production of the energy source, also save energy and also recycling capability of electric batteries and all those things, and broad temperature range we can work with these technologies. So this is our demo video recently published based on our project Astrobat. So currently we are in the stage of material production, and manufacturing stage will come in the coming years to develop these batteries for getting higher TRLs, that is technology readiness level for the industrial sectors. So basically, I would like to show you this value chains, how the application sectors are dividing. So basically, the applications sector, automobiles, health, and industrial electronics, and also digitalization. These are the main application sectors which is focusing for the future generation. And if we separate a smart product and systems, there are two groups: hardware modules and software modules, and also component ICs, MEMS package, and all those things, and SW software technologies for various development of new technologies, EDA technology and manufacturing technology, and electronic value chains and materials, equipments, SDKs, and many other compilers, debuggers for software to support faster the design files to get new products and new application in future generation. These are the electronic value chain for industries to develop how focusing for a product in future applications and all. And this is, I would like to show the driverless autonomous car, which is transparent. You can see the pictures. This is a transparent factory of Volkswagen. It is very close to my apartment. It's just a walkable distance from here. So we have a good association with many automobile sectors of Germany with the Fraunhofer IKTS. And these are some of their model car without driver. In future, they are planning to make a driverless cars with a secured driving, and all these activities is coming in good with electrical performance. So the plan is to reduce the fuel like petroleum products, and use electric vehicles to reduce the carbon dioxide emission, and all those aspects as in main agenda for transportation sectors in Germany. So when I club with 5G and 6G telecommunication, so this is another project which is integrated with this technology sectors. That is the 5G to 6G switching. This is one of the project we are actively participated, and my work is actively involving this kind of activities. This is a demo video for project of 6th generation electronics, how the telecommunication is developing for the 6th generation. So I will show this video and explain a little bit about 6th generation. And this video is made by University of Oulu and the 6G flagship program, how the future infrastructure for the IoT, radio, and other communication, transportation. So you can see that how virtually we can communicate to the world in everywhere, in the air or in ground, and also we can good health system to easily everyone can contact their personal doctor without moving to the hospitals and checking with the house itself, and also virtual reality for designing, and we don't need a laptop or a mobile for using our technology in the future. Everything will be virtual platform, and everything we can do it with this 6G implementation. These are the focus for the 6th generation technology. So basically we are working for the devices, what are the requirements for the 6th generation devices and printed technologies, and all those things to these technologies are linked with the main applications like automobiles, hybrid, electronics, microelectronics, and all other sectors which support the target of different areas. So easily we can connect each and every automobile in the network, and we can easily target and with a good security, and we can easily network in the cloud network, and everything should be very easily we can attain at a very fast time. We're looking with the high frequency switching of electronic equipment. So that's the main goal of the sixth generation, to speed up the electronic switching, to get a faster communication, to get a cloud network is a reality for the future. So this is the story behind the 5G and sixth generation switching. So you can see that many future goals, the meeting planning and future, we can easily all part of the world will communicate each other, and every section and everything, all part will be communicated as a switch, and autonomous in the instrumentations and autonomous transportation. All these structures are basically from this wireless communication advancement in the future, and these are the technology looking for the future for the sixth generation technologies. So basically, so I would like to switch to the next slide. Now I think it's going to end soon, and it is just showing about the application and future aspects of telecommunication, how it is going in future, all those things. You can mostly everything happen in autonomous from fifth generation to sixth generation. So these are the target and vision for the next generation people to utilize their electronic gadgets and their day-to-day life with this network technologies. So I'm just stopping these videos and just skipping for the to show the different generations of telecommunication and the basic principles behind it, and what are the target for today's communications and the different technologies, how it's going to achieve for the future. And you can see that from sixth generation wireless communication beyond 4G and 5G, and why it is, you can see that from first generation in 1980s with the handset, you can see, and second generation 1992 they reduced the device, and third generation further reduction. Nokia developed a new technology for the reducing semiconductor technology integrated with this wireless communication gadgets. Then fourth generation is made with displays and many other activities and many new OS coming to improve the operation of our telecommunication gadgets. And basically 5G is looking for the increasing the speed of operation to get a faster communication, faster than fourth generation network. That is currently we all are using this, experiencing this technology in the worldwide. And 5G is many places in Europe and European countries, they are implemented many of the cities to fasten this operation of telecommunication networking. And 6G is basically coming from the drawbacks of 5G. So actually 5G is implemented with the existing technology of manufacturing devices. But when we look for the sixth generation, we are achieving to have a high or a very high speed of operations. Basically from high frequencies, so for till 4G we are utilizing only less than 6 gigahertz frequency to operating for normal wireless network applications. But for 5G and 6G, it is going to high, and it is targeting for above 10 to 300 gigahertz or beyond 300 gigahertz. These are the target for the 5G and 6th generation implementation of new cloud networks for the future applications with a target speed of 1 Gbps. So you can imagine how faster our technology will move in that goal. So in order to getting that much speed, we need to focus on our device. And when we look for a device, the materials are the basic building for every device and its operations. So there are many mandatory requirements for this 5G technology to implement it. So I just made a chart which is connected this different generations of technology with ceramic, multi-layer ceramic packaging, which is associated with the telecommunication. So basically, HTCC, LTCC, I already explained in the before slides. High temperature coated ceramics in the first generation network gadgets, they are utilized this kind of with the requirement of property limits. And for second generation device, it's splitted to HTCC and LTCC. So the new two technology came, that is, I explained before, to reduce the fabrication cost of the devices, LTCC came. And these HTCC and LTCCs are here for till for 2015, which decades of operation to implement this 4G, 5G networks and all these are utilized. Here and for the sixth generation, we are introducing a new technology, that is ultra low temperature coated ceramic technology, that is recently developed in the world, and we have upper hand for this technology. And we basically, I have done my second doctoral degree based on these ultra low temperature coated ceramic technologies. Maybe I will discuss this in the future slides. Basically, when we go for a different level of generation, basically we are increasing the speed of the device by reducing miniaturization, also keeping the device speed. So basic requirement when we connection with a electronic device, basic property of controlling the miniaturization is the permittivity. The same time, the low permittivity material increases dielectric speed. So these are the main targeted area to focus to develop a new materials and gadget with ultra low temperature coated ceramic section. So basically the focusing for very low permittivity materials, very low dielectric loss and very high microwave frequency applications, and in connection with the good thermal properties and high thermal conductivity and low CT for making hybrid devices with conductor and ceramics and other supporting device with PCBs and all those things. We needed to introduce new material which focus for 5G and 6G. Basically, I would like to explain more about ULTCC technology capability that I am working in this area. How we are achieving this sustainability goal with the ULTCC technology. So I'm moving to the next slide. So we can start something about the evolution of HTCC and LTCC technology. So you can say the first tape casting was reported in Europe. Tape casting machine and principle is reported in Europe, and the first high temperature coated tape is developed. That basically this tape technology is used for making the high temperature coated fabrication. That is nothing but the ceramic particles are mixed with a polymer material binder and make in the form of tape. You can see that ceramic tapes example, and use these tapes to make a multi-layer stacking and lamination and firing to introduce many functionality like antennas, capacitors, and many other inductors, passive and active components for making reality this wireless communication. So the very first materials we reported in the patent is magnesium, is the magnesium silicate composition, which has a sintering temperature of 2100 degrees Celsius. You can imagine that how high temperature we need to fabricate a high temperature microelectronic component for supporting this telecommunication application. I'm just focusing for telecommunication application because most of these products are utilized for telecommunication sectors. In 1945, this is the first development of tape casting. After that, in 1946, fabrication of thin ceramic sheet capacitors based on titanate, barium titanate, and titanium dioxide, which has temperature, fabrication temperature of 1200 to 1350 degrees Celsius. Still, it is above 1000 degrees Celsius. So after many years, in 1970s, IBM Corporation first introduced the LTCC technology. That is basically they are mixing the ceramics, high temperature ceramics with the low melting glasses to reducing the fabrication temperature of these products. And basically they achieve the target of 760 to 952 degrees Celsius. And basically you can see the products developed at LTCC technologies. And basically these are utilized till for fourth and fifth generation technology, utilizing this HTCC and LTCC technology. So I would like to switch the needs of a new technology. So basically the demand of this technology is very high because this technology provide a unique solution for high interconnect density. That means we can integrate many active and passive devices with this technology, and we can many consumer and other application sectors eagerly looking for new integration of material to develop this kind of electronic components. So basically these HTCC and LTC technology utilized for mobile phone handset, wireless module, automotive electronics, military electronics, medical electronics, GPS radar, wireless LAN, and all these gadgets are really connected to all sectors of application that I addressed previously. And these markets, especially in European hybrid circuit markets, you can see that it is increasing every year with a huge demand based on the technology requirement and the new focus of technology and switching of technology, all those things. So I would like to talk about the evolution of ULTCC technology, pointing towards the drawback of HTCC and LTCC technology. So you can see that high processing temperature starting for LTCC and HTCC from 700 to 2000 degrees Celsius. Electronic wastage issue, because after the use of our product, totally these things are electronic waste, like our handset and all those things are electronic waste. We cannot refabricate these ceramic components back to new applications. So these are the one, because of high temperature, we need a very high processing temperature to refabricate or recycle this waste. So costly recycling, then environmental issues, many hazardous materials which are using for tuning this property for the technology requirement, and high energy consumption due to high temperature operation, carbon dioxide emission, and these are the main drawbacks of HTCC and LTCC technology with the industrial requirement for the future, at least for the next 10 or 20 years, looking for how the technology is growing up. So based on this drawback, and we started to evaluate starting from 2014, and we made a solution to reduce the fabrication temperature well below 700 degrees Celsius. The processing temperature of devices should be 200 to 700 degrees Celsius. So if we keep the fabrication temperature in this range, we can easily integrate the printed circuit board that is fabricated at this temperature. Also the same ceramic we can integrate it with this technology, and we are achieving for fabrication cost, reduce or decrease of fabrication cost, carbon dioxide emission by reducing the temperature, recycling temperature. We can easily recycle after the use, because these temperatures are very low, and with less manufacturing cost we can develop these temperature at industries. And environmental issues, utilizing many for example lead cobalt based material utilized for many electronic applications currently, and these are the new regulation based on circular economy. So this regulation is focusing to reduce the environmental pollution with to eliminating these hazardous materials from the electronic gadgets. So looking for ULTCC technology, starting from high temperature to ULTCC technology. So basically, the main requirement for the high temperature to ultra low temperature technology is these ceramic based materials need a hybrid platform to integrate conducting channels by electron conductors like silver, gold, copper, and many other high temperature conductors. These should be integrated with ceramics. So we need to keep in play with the many high temperature and thermal properties to tune this property to make a good property for ultra low temperature coated ceramics. So far, since 2010, there are many researchers worldwide reported many material composition, nearly 300 material compositions are reported for ULTCC range. And out of them, you can see that most of the material reported are 47% are ceramic, 11% are glasses, and 42% are composites. Basically, ceramic plus glass will come in composite fabrication. And if we look for the material family, you can see that among this material family, there are 54% of molybdates, then 20% vanadate, then 11% telluride, 8% of tungstate, and other materials also utilized for this ULTCC technology for the realization. So these are the current status of ULTCC technology. So I would like to move to my research on ULTCC technology. In 2019, we have developed the very first ULTCC devices in the world, that is developing a 400 degrees Celsius a wireless LAN antenna with this ceramic technology. So this is our first report on this material. It is a titanate based material utilized for wireless LAN application. We demonstrate to fabricate an antenna at 400 degrees Celsius, which is beyond this HTCC and LTCC technology. So these have same and good improved performance as compared to HTCC and LTCC technology. So ACS Sustainable Chemistry and Engineering accepted our work in the journal in 2019, and they taken us our publication as a cover page for their 2019 cover page for their publications. So another important thing is ULTCC research is sixth generation development. Basically, this sixth generation is to remove the drawback of 5G networks that presently used with the existing technology. So I have made my second doctoral degree thesis on ULTCC technology. So the 6G flagship program of Europe, especially in Finland, they selected us my thesis as the sixth generation development of electronic gadgets. So I reported many material composition in that thesis to develop various to show the capability of ULTCC technology for various electronic gadgets. For example, I made a piezoelectric material sintered at 400 degrees Celsius, and also some glass compositions fabricated at 300 degrees Celsius, and all these things are supporting for this existing technology, bring down the fabrication technology low to 400 to 500 degrees Celsius, which is beyond HTCC and LTCC limits. These are the targeted goals. So that's the reason they selected my research output and publications and all my research activities as connected with the 6G flagship program of University of Oulu in 2019. So the focused and strategic research of present and future goal is my goal with my group in Fraunhofer IKTS is to develop transformers, sensors, inductors, power electronic devices, microwave components, MEMS, actuators, hybrid circuit resistors based on ULTCC technology. Basically, I am focusing to low-cost fabrication low fabrication temperature, and environmental friendly material to remove the hazardous material for the electronic gadget manufacturing for future generation. Basically, easy of recycling for low temperature systems, good thermal, mechanical, and electrical properties as compared to the high temperature and low temperature material fabrications. Basically, our targeted sixth generation material plants are for tapes, electronic packaging, and devices. These are the main goal, and we are going to achieve ULTCC dielectrics, ULTCC magnetodielectric, ULTCC magnetic material, ULTCC solid state batteries, ULTCC metamaterial, ULTCC functional components, and ULTCC EMI shielding, ULTCC 3D and 4th dimension printing. These are the target for the future generation development, and most of my project is related to this ULTCC technology, and we are going to achieve higher levels of TRLs in the future steps to get introduce this technology to the world and develop a sustainable future and keep the circular economic concept of our agenda. So these are my expertise in ULTCC technology. Nearly for the last 5 years, I published nearly 11 publications based on these ULTCC technologies, and few patents are still under filing range, and also nearly 5 books I have authored in dielectric materials ranges, and projects basically worked nearly 5 to 6 projects worked on materials and sustainable material production for various applications. So my visibility is in material research, nearly 30 plus publications I have published in various international journals with a last 5 year H index of 30 Google Scholar from Google Scholar and Web of Science report, and nearly 27 international conferences I attended from various parts of the world with my material research and new technology, and all those things are the targeted future research to widespread visibility to the new technology to the all over the world. And these are my first patents which during my first doctoral degree. Then these are the book chapters I published during my studies and research during my career. And basically, I am a reviewer board member of 16 SCI journals, and also a review member of France Research Society and National Science Center Poland. I am reviewing a project proposal, the new project proposal for these national agencies. And 2020, I am advisory editorial board of dielectric ceramics for electronic application. It's a front in materials section. So I am editing this for the new publications for the new world. So we want to get a high visibility for new dielectric materials and electronic devices for the future application to fulfill our future 6th generation emissions. So these are the website and research profiles in website, and you all can contact through from various channels of research networks through this. And basically, I'm coming back to my personal zone. Thank you all for the attention. And this is my family. And last year we crossed the Arctic Circle of Finland with my family, my son and my wife, and we stay Santa Claus village at Finland. And my hobbies are fishing, and this is ice wall fishing during winter time at Finland. This is also summer fishing in Finland. And I'm a cricket player, a left-handed batsman, all-rounder player for national German cricket team. So I'm part of, now I'm playing as a part of RCD Dresden is our Dresden city team, RCD Dresden cricket. So we have a couple of indoor 2020 and 50 one-day matches going on around the national levels, also across over the Europe, and also I my other personal activities like hiking. I like walking, cycling, hiking through the various part of the Dresden. So I conclude this section and thank you all for the attention.
Yes, thank you so much, sir, for a very informative session. So now we have a few questions in the chat box.
Yes.
So we'll take up them quickly. So the first question is from Piyush Gaur.
Okay.
So he's asking that which ceramic material is used in LTCC and HTCC?
So basically HTCC applications, alumina. The pure aluminum oxide powder is used as a high temperature coated application. You can see that alumina is the high temperature coated ceramic material which is abundant in nature, and its fabrication temperature is nearly 1600 degrees Celsius. That's the reason it is in the category of HTCC technology. When we go for the LTCC technology, so they reduce the fabrication temperature by adding the highly durable and property compactable glasses to form alumina to reduce the fabrication temperature below 1000 degrees Celsius. So alumina plus some ceramic glasses used to reduce the fabrication temperature of alumina bring in order to on the same time, if you're reducing the fabrication temperature, we need to keep the technology requirements. So these glass and alumina compositions are used for LTCC technologies. So here the next ULTCC means, so we are adding a low fabrication temperature glasses to reduce the fabrication temperature, bring down below 700 degrees Celsius. That is the ULTCC technology. And many material, depending on the permittivity and dielectric laws, we select many material for various applications for these technology applications.
Okay, so moving to the next question from Amil. So what is the impact of HTCC and LTCC evolution on energy consumption and time processing?
This was a good question. Basically, the evolution from HTCC to LTCC basically targeted for reducing the cost of production. For example, HTCC, if you use a high temperature furnace for 1600 to 2000 degrees Celsius to develop a module, we need huge amount of time and also energy for working one furnace at very high temperature. So if we fabricate a LTCC technology at a lower temperature, for example 900 degrees Celsius, we need a less energy for the utilization of the temperature. So we need less energy so that we can reduce the fabrication cost. This will reflect the reduction of cost, and same way the time consumption, I think time we cannot reduce, but new technology like additive manufacturing and fourth dimension printing and all this technology we can integrate to this ULTCC and LTCC technology. And here is the more impact to reduce the time management. So we can very fast we can produce one develop material. But for HTCC and LTCC, the main drawback is we can only achieve the cost of production. So we cannot control the time much. But of course, LTCC technology is reducing the time of production little bit, but still we need to fabricate very fast development. So that's the reason we need new technology and new systems and new devices for fabricating new devices and with the technology requirement.
Yes, thank you, sir, for your reply. So next question is from Piyush Gaur. So he's asking that are we using crystalline material or non-crystalline ceramic?
Actually, the glasses are amorphous compositions. When we cinder at a high temperature, these glasses are crystallizing. So majority of the compound like alumina is a crystalline, pure crystalline. For example, pure glass we use when we during the fabrication stages, These glasses are melted and recrystallized during the manufacturing process. And during these stages, all the materials are polycrystalline and form a bulk components at LTCC and LTCC ranges. This is the current scenario of developing of ceramic-based components, packaging components.
Okay, thank you so much, sir. So any other question from the participants? So we still have time. You can either write them in the chat box or you can unmute yourself.
Okay, sir. I have one. Okay. Sir, first of all, very interesting presentation, and researchers can be interesting, and too, you showed that, and sportive too. And not all researchers are boring like me. And my question was related to the funding. Does your institute support Indo-German exchange fellowship programs?
Yes, it is happening. I think now I am currently discussion with CSIR, CMET, and some standard IS standardization institution in India to make a DST German funding to make some kind of bioeconomic product based on this LTCC and ULTCC technology. So we are now in discussion with this project, and there are many open projects for indoor development, and also battery projects and also e-waste management, and there are many projects currently running with India and Germany for developing the infrastructure and technology for reducing this circular economic concept in India.
So, do the institute have to have a prior MOU with the institute before the student?
Actually, we don't have. Sure, for exchanging the technology, we should write MOU with both the institution and basically
student exchange program.
Basically, in our organization, we don't use. They have some internal regulations and many security restrictions for the technology that they are developing here. So we have very less. Only we take a very few students for their part of their project for like master student projects. And also that is also connection with only in German universities, and also PhD students we hire only those who are associated with the German universities, but we don't directly take any students from India because we have some kind of security restriction and some internal regulation for hiring people from internationally.
Okay, sir. Thank you. Any more questions from the participants?
Yes, sir. I have just one question to you.
Okay.
Yeah. So at the end of your session, I would like to, get your insights on the recommendations to the people who are working in this area, to the researchers. So any recommendations?
So basically,
yeah.
So basically, my recommendations are we have a huge limitation of infrastructure like materials, and we all when I done my degree in India, so we all importing this raw material from other countries. For example, we are importing this raw material from Aldrich and many other countries, but we are not developing any materials or many material purifying in our country. Only few material that is targeted for example, Atomic Research, Baba Atomic Research Institute and ISRO. They need some kind of high pure material. That is the only focused material they are developing in India, but there is no much because IR is developing few materials, but I don't know how IR is visible in India, internationally. Because material production is one of the important points, as you can see that China, how they grow their country, because they manufacture everything their country with their resources. That's the reason they are developing and they are making good global connection, and they are making profit, and all these export values, everything they achieved by they increase their manufacturing and production in their country. They utilize their local manufacturing high. So instead of buying everything from outside, we need to sustain ourselves. We need to develop everything for ourselves. So the same strategy is for Europe and Germany. I found that. So basically, we need to develop from 0 to 1 by our country. So then only that's my idea to how we can grow in the future for the all sectors.
Yes, thank you so much, sir, for sharing your recommendations with us. So we can take one last question. It has just popped in the chat box. Okay. So the question is from Piyush Gaur. So he's asking, yes, sir, I'm working on memories. So any suggestions to make a design with ceramic material like HTCC or LTCC? Can these materials be used for high switching?
No, especially these ceramic technologies are basically it's a package or for example, MOSFETs or many kind of ferroelectric memories, and all kind of memories are a supporting device, or it is after the development of memory devices, the ceramics used for pack this material to retain its capability for long life. So we cannot use this without package, this developed MOSFETs or this kind of semiconductor device or memory devices. Without this ceramic package, we cannot use it for the many applications. So these are the main. We cannot use this technology for manufacturing the memories, but this is a supporting package to all semiconductor and all kind of electronic active and passive components.
Okay, so thank you so much, sir. So hopefully your answers will definitely benefit Piyush Gaur to his queries. So thank you. We are closing the session now. So today we'll be announcing the results for lockdown diaries. Like this was a competition, which was a blog writing contest, which was opened up in the mid of September, and it was held in the September month. So with our guest speaker, so sir, now I request you to announce the winners. And Rishabh, I think you can take over. Yeah.
Yeah, I will take over. Just let me share one slide. Okay. So as you know, this year started with the virus, and virus led us to freeze all the things, and for some of us it is has been worse, and others took that virus as the opportunity and started with this new beginnings, or today are people calling it as a new normal. So it has many interplay of positive and the negative feelings. So whatever happens, that we are going to overcome these opportunities, and in this era, so most of us students are at home and have their own lockdown stories, how they overcome these opportunities and have the motivation about it. So we invited entries in the month of September. And so today in the IEEE week, we are declaring the result of these entries. And these entries will be winning entries. We have selected 3 winning stories, which will be published onto our website. And the first winning story will be published on the IEEE Photonics, IEEE Prakash Bharati website also, and as well as circulated among the all India level. So I would request now Professor Dr. Jobin to share the results with the audience.
Okay. So first I will publish the third prize. I think third prize goes to Aryan. The topic of blog is a page from my diary. Should 2020 be erased? That's a third prize winner, Aryan. So I wish all the best for him.
So Aryan, you can turn on your video. We can have a photograph of it.
So congratulations, Aryan.
Congratulations, Aryan.
Great job.
Yeah, thank you so much, guys. Thank you so much.
Then maybe, so should I announce the second?
Aryan, are you coming up on the video?
Yeah, I'm there. Just a minute, actually.
Okay, fine.
So Aryan, wrote a story about its diary and shared the thoughts on its diary. And so this story will be available on our website very soon.
Okay. It's good to know because I also like to read the stories.
Yeah, we'll share the link with you as well.
Sure.
Aryan, I think there is a video issue at your end.
Yeah. So Risha, we can take the photograph.
Yeah, we can take the combined photograph later. So
so next second prize I will announce. It is Harish Swaminathan, and his story title is Good Food Brought Togetherness, Fun, and Blossoming the Friendship at D74. This is the title of his blog. Harish Swaminathan. Congratulations, Harish.
Harish.
Thank you all. Thank you so much.
Okay, so you can turn on your video and we can have a group picture. Yeah. Okay.
So I'll move to the first prize. Anchana Bhattacharya. Story of her blog is Nunchunks to German, kicking up a storm in lockdown.
So congratulations, Angana. She's from IIT Guwahati.
Congrats, Angana.
Thank you so much. Thank you so much for appreciating me.
Congratulations.
Yes.
So on behalf of IEEE AcSIR-CSIO team, I congratulate all the winners.
Thank you.
Thank you so much.
congratulations to all.
Yes, so I request all the winners to turn on their
Thank you
video.
so much.
And I request our speaker as well as our participants if they can turn on their videos and we can have a group picture to make this moment memorable for all of us. And I also thank all the participants who participated in this event. And we look forward to your participation in other upcoming events of IEEE AcSIR-CSIO. So stay updated at our website and our social media handles. So Rishabh, I think you can stop sharing your screen.
Yeah, I'm doing that.
And we can have a group picture and we can close the session. And thank you, Jobin sir, for this great session and for being our guest today. It was a great and knowledgeable session. Thank you so much.
Thank you. Thank you very much. Okay, bye.
Yes, Rishabh, are you? Yeah.
So wait.
Okay, sure.
So I request our participants to turn on the video. I'm happy to share that we had international participants also for this session. So in spite of the time zone difference, still they are joining us. So thank you everyone. And we look forward to your participation in our coming events.